During projectile motion, the center of mass follows a smooth trajectory. Projectile motion is affected by three biomechanical factors. 1. Projection angle, 2. Relative projection height, and 3. Initial velocity. The optimal takeoff angle for this fine diver is between 45 and 90 degrees. This is because she is trying to go as high as she can in order to get as much flight time as possible, but she must also have enough horizontal motion so that she does not hit the board. At the peak of her trajectory, her vertical velocity is 0 meters per second. Throughout a projectile motion, we assume that the horizontal velocity stays constant, though this is not necessarily the case. We disregard any possible air resistance, which would change both the horizontal and vertical velocities. At equivalent heights on either side of the peak height of the trajectory, the vertical velocity will be equal and opposite. If the vertical velocity was 4 meters per second here on the left side, it would be negative 4 meters per second here on the right side. In reality, there is air resistance, which creates a drag force on the body during flight. And this air resistance causes an oblique trajectory rather than a parabolic trajectory.
The next topic we will discuss is momentum. Angular momentum equals moment of inertia times angular velocity. When there are no external forces, such as when the diver is in the air, the momentum is conserved. Once the diver is in the air, all she can do is alter her body position to adjust the moment of inertia, thus changing angular velocity. Moment of inertia is defined as resistance of a body to rotation about a given axis. The moment of inertia changes with position and can be represented by the equation I equals mr squared. The straight position has a greater moment of inertia than the pike position, which has a greater moment of inertia than the tuck position. This is due to the difference in distances from the axis of rotation to the proximal end. The moment of inertia also changes depending on the axis of rotation. Here we can see that the diver is rotating about the transverse axis. Then she comes out of the somersault and begins to rotate around the longitudinal axis, which can be seen by the twist. She then stops the twist and continues rotating in a somersault. The moment of inertia is different for each part of the dive, but the angular velocity also changes in order to conserve angular momentum. In a system, the total momentum stays constant when there are no external forces acting on it. When the angular momentum of one body part changes, this will cause a change in momentum in another body part, resulting in the net momentum of the body staying constant.
Next, we are going to talk about drag force. When in the air, the position of the body when falling influences the effect of air resistance. When the body is in a tuck position, there is less air resistance because the surface area is smaller. The diver can change the position of the body into a straighter position to increase surface area, which will increase the effect of air resistance and slow down the body to prepare for the clean entry. At entry, the diver uses streamlining to reduce turbulence and pressure drag. Turbulence is defined as a non-uniform flow of fluid around an object, while pressure drag is caused by a pressure differential. Streamlining the body when entering the water reduces both turbulence and pressure drag. Turbulence by causing the flow to remain laminar for longer. The coefficient of drag by having less surface area.